Hey, this is Mr. Bennett, and we are starting Unit 3 of Conceptual Chemistry. We'll be talking about the atom. So video 3-1 is the structure of an atom. Now to get us going, I want to talk about atomic theory. Atomic theory is the idea that an atom is the smallest particle or piece of an element. If we go all the way back in history to the Greeks came up with this idea of the atom. They had the idea that if we took matter and we just kept dividing it and dividing it and dividing it into smaller and smaller pieces, eventually we get to this tiny little piece of matter that was indivisible and indestructible that they called an atom. How small is an atom? Well, it would take 100 million atoms in a straight line to form an inch. So if we were to draw with a pencil an inch long line, that's 100 million atoms. For a penny, if it's made out of pure copper, it would require 2.4 times 10 to the 24th atoms to make that penny, or this many atoms. That's a lot of zeros. Now the guy who basically put together this atomic theory, his name was John Dalton. He's an English scientist who lived between 1766 and 1844. He came up with atomic theory that had 4 different parts. First part was that elements are composed of tiny, indivisible particles. Atoms were second part. Atoms of the same element are identical. Third, atoms of different elements combine to form compounds in whole number ratios. Well, what does that really mean? That means that, for instance, water, which is H2O, is really made up of 2 hydrogens for every 1 oxygen. Another example would be, for instance, carbon monoxide. Okay, carbon monoxide is made up of 1 carbon for every 1 oxygen. Notice neither one has half of an atom. There's no half an oxygen or half a hydrogen. It's always whole number ratios. A fourth idea Dalton came up with was the idea that chemical reactions do not change, create, or destroy atoms. We simply rearrange them. So in other words, when a chemical reaction occurs, you're taking the atoms that are in each compound or each substance, and you're simply just rearranging them between the different compounds. You're not destroying them, you're not creating them, and you're not turning, say, hydrogen into another element like oxygen. You're simply just rearranging. Okay. Now these guys in red up here, indivisible and identical, these ideas have since been proven wrong. So today we're going to talk about this divisible idea. So it turns out atoms are divisible. If we take an atom, we can divide it into 3 different subatomic particles. You have a chart in your notes and you're going to fill this in. So if you need to pause it, pause it. But protons, they have a charge of +1. Neutrons have a charge of 0, no charge whatsoever. Electrons have a charge of -1. Together, these 3 subatomic particles make up an atom. Now mass-wise, this is the charge, but mass-wise, protons have a mass of 1 AMU, neutrons have a mass of 1 AMU, and electrons have basically no mass. They do have a tiny little bit of mass, but it's so small that we can basically consider it 0. Okay, so just think of it as protons are 1, neutrons are 1, electrons are 0. So what's an AMU? Turns out that AMU is short for atomic mass unit. It's a unit used to measure the mass of a proton since their mass is so small. We don't want to do it in grams because this is how tiny it would be. This would be a super difficult number to play with. Instead, we can just say the mass of a proton is 1. To calculate this, they took carbon-12, which is the most abundant version of carbon, and then they figured out the mass of 1/12 of it. Now, if we take a look at the atom, one of the major ideas that we need to talk about is the idea of an atom's nucleus and what the nucleus is. So that's going to be our next idea here. And the scientist who's responsible for our understanding of the nucleus was Rutherford. Okay? So if we look at my picture over here, we have tiny little nuclei. And on your handout, you have little pictures of atoms with tiny dense nuclei in the center. Okay? So let's talk about Rutherford's experiment. Rutherford's experiment used something called an alpha particle gun. Alpha particles are these tiny little particles, okay, and they have a positive charge. So what Rutherford did was he fired this alpha particle gun at a super thin sheet of gold. Alpha particles, when they come in contact with the screen around the gold, cause it to glow. Okay? So what he did was he fired his alpha particles, which again are super tiny, smaller than the size of a gold atom. Okay? He fired it at the gold. And what he found was that most of the alpha particles shot straight through. But every once in a while, an alpha particle would collide with something and it would be deflected off to the side. So that's what these 3 lines are. Okay, so what I'd like you to do on your diagram is pause this for a second and draw some alpha particles going through from left to right and show how they can go by a nucleus or they can occasionally impact a nucleus and be deflected off to the side. Okay. So that's what he found. Alpha particles would zip through the gold. In fact, he thought they would all be deflected, but he was kind of shocked by the fact that most of them shot straight through and only some of them were deflected. So if we summarize his observations, he found that most alpha particles passed through, they were not deflected. Only some of the alpha particles bounced back or were deflected. Well, what does this mean? Well, his conclusion was, first of all, that most of the atom is open space. Hence, most of the alpha particles were able to shoot straight through. The ones, or the alpha particles that were deflected, must have come in contact with a dense center. So he had the idea that at the center of the atom, there was this really tiny center with a lot of density. In fact, most of the atom's mass was stored there. And that it had to have a positive charge. Now, the reason why he knew it had to have a positive charge is that when we deal with charges, like positive and negative, if you had a positive and a negative, they would be attracted to each other. They would stick. But if you have a positive and a positive, they repel. So he knew the nucleus had to be positive because alpha particles are positive, and that's the only reason why it was deflecting and not sticking. So the eventual definition of a nucleus is that, first of all, it's a tiny central core of an atom. It's extremely dense, so dense that it contains most of the atom's mass, pretty much like 99.9% of it, or whatever that is. It's composed of protons and neutrons, and it's held together by nuclear forces. These guys are important. Okay, you need to know what a nuclear force is. Okay, the idea behind a nuclear force is that, generally speaking, as I said, like charges, when they get near each other, they repel. Okay, and this kind of, like, Rutherford understood this, and this kind of mystified him, because if the nucleus was in fact dense, and it contained a lot of particles that all had the same charge, and they were all positive, then it should fly apart. Nuclei should be completely unstable, and they should just, like, explode. But that wasn't the case. What Rutherford found was that they stuck together. So that led to the idea of discovering nuclear force. Nuclear forces turn out to be stronger than the repulsion, meaning the force that's causing positives to zip away from each other. It's a stronger force. But the problem is nuclear forces also have very, very short ranges. Very short. Okay. So my analogy for this is if you think about two magnets. Magnets have poles, right? They have a positive side, they have a negative side. So imagine you've got the positive side of two magnets and you're trying to push them together. Normally, as you get them close to each other, they would repel. Okay? But now imagine that you put some Velcro on the magnets. Okay? So this side you've got the little pokey, stubbly side, and then on this side you've got the fuzzy part of the Velcro. Okay? So now, even though right now they're being repulsed, okay, if we get them close enough, if we get them right next to each other, so they're just about touching, and the Velcro can connect, the Velcro will hold the two magnets together and prevent them from repelling each other. Okay, nuclear forces have very short range, like Velcro. So you have to get them close, but once you get them close, they are stronger than the repulsion, and they will stabilize and hold the nucleus together. What about the rest of the atom? Well, as we said, most of the alpha particles pass straight through. That means that atoms are mostly empty space. Okay. Turns out, in that outer area, the empty space, all you really find are electrons. They're orbiting the nucleus. So alpha particles, as they shot through, they were just going straight through that orbital area where the electrons hang out, also known as the empty space. We'll talk more about electrons in Unit 4. Now, the last concept I want to get to is how are elements different? Elements, meaning hydrogen, helium, lithium, anything on the periodic table, how are they different? Well, first idea is they have different atomic numbers. The periodic table is actually organized by atomic number. So hydrogen is number 1, helium is 2, lithium is 3, beryllium is 4. And it turns out that the atomic number is actually determined by the number of protons. Hence, these guys are the same number, 1, 1, 2, 2, 3, 3, 4, 4. Neutrons, on the other hand, not so much. Okay, we'll talk about why these numbers are the way they are, but notice there's no real pattern here. Okay. Mass number, same deal, no real pattern. However, if you look closely, what you should see is if I add these two together, I get the mass number. Same thing here, if I add these two together, I get the mass number. These two, 3 and 4, get the mass number. 5 and 4, again, I get the mass number. We'll talk about this in a second. Electrons, notice they're always the same number as the protons, 1, 1, 2, 2, 3, 3, 4, 4. That's because we're talking about neutral atoms right now. Okay, if they're going to be neutral, that means that the number of positives needs to add up with the number of negatives So the positive charges plus the negative charges needs to add up to equal 0. So that's why we have, if protons are positive, electrons are negative, 1 and 1, it ends up neutral. 1 positive, 1 negative. 2 positives, 2 negatives, again, it's neutral. Okay, so to understand that previous chart, we need to talk about a couple different ideas. The first one is atomic number. Atomic number identifies the type of the element. So this idea right here, this tells you what element you're looking at: hydrogen, lithium, potassium, gold, etc. And it turns out that the atomic number is always equal to the number of protons in the nucleus. So what does this really mean? Well, it means that the protons, these guys, they determine the element. So they are the deciding factor as to what element you're looking at. Okay, if you change the number of protons, you change the element. So I'll give you an example here. If the atomic number is 2, that means you have 2 protons, and that means you're looking at helium. Helium is the only element out there with 2 protons in the nucleus. If you take 1 proton out, it becomes hydrogen. If you add a proton, it becomes lithium. Okay, helium is the only one with 2. Now you have a picture of this on your paper. What I'd like you to do is label this 2 as the atomic number. Okay, so before we talk about this number here, I do want to talk about one more time, just to reiterate, neutral. Atoms are neutral. Okay, they can be non-neutral, they can be negative or positive, but the atoms we're talking about right now are neutral, which means the number of positive charges, the protons, will be equal to the number of negative charges, the electrons. Okay, number of protons equal number of electrons, you get a charge of 0. Okay, so in this case, if helium is going to be neutral, we look at this atomic number, and that also gives us the number of electrons. Now, the other number, that 4 up top, we call that the mass number. There's another name for this. It's also called the atomic mass. Okay, and what this gives us is the number of particles in the atom that have mass. Well, if we go back to that chart that we filled out earlier about masses, there are 2 different subatomic particles that have a mass. That'd be protons and neutrons. They both have a mass of 1 AMU. Okay, so your mass number, your atomic mass, is simply just the number of protons plus the number of neutrons in AMUs. So in this case, I'd like you to label in your picture that the top number, the 4, is the mass number or the atomic number. Okay, and if we look at those numbers, it turns out we can use that to determine the number of neutrons. The mass number minus the atomic number will give you the number of neutrons. Why? Like, why is that? Well, the mass number is really equal to the number of protons plus the number of neutrons. The atomic number is just the number of protons. So if we take this and we subtract this, the protons will cancel out and you're left with neutrons. Okay? Now if you look at it this way, and you do need to be able to read an element that's written this way. If I write an element this way, you need to know that this is the symbol that tells you the element. That's the element symbol. Okay. Again, this is the mass number. Okay. And this is the atomic number. So you need to be able to recognize this and understand what it means. Well, it turns out, since the mass number is on top and the atomic number is on the bottom, you can actually handle this like a math equation. You take the top number, you subtract the bottom number, and that will give you the number of neutrons. Oops, neutrons, which in this case is equal to 2. Okay, let's do a little practice and then we're done. So our first problem we're going to do together, this is what we call carbon 14. First thing we want to know is how many protons. Well, we said this bottom number, this is the atomic number, and this is what determines the type of element you're looking at, as well as determines the number of protons. Okay, so that would be 6. Now, if I gave you the atomic number of 6, you should be able to go to the periodic table, look up the atomic number 6, and tell me that it's carbon. Okay, because again, the periodic table is organized by atomic numbers. Now, if we want the number of neutrons, we simply take the top number, which is the mass number, and we subtract the bottom number, the atomic number. So 14 minus 6 gives us 8. Okay, and then last but not least, electrons. Since this carbon is neutral, that means that our protons, which are positive, have to be balanced out by electrons. So we have 6 protons, which means we're going to have 6 electrons. What I'd like you to do now is pause the video and try the other 2. Try them first, and then if you get stuck, you can start the video, or if you get an answer, you can play it again and check and see if you got it right. So pause it now. Okay, I'm assuming you paused it. Let's talk about the remaining problems. So here we have barium, 137. Okay, So 137 is the mass number, and then 56 is the atomic number. Now remember, the atomic number is the number of protons, so that's 56. Okay, to get neutrons, we simply take the top here, subtract 56. That's going to give us 81. And then since this barium is neutral, that means the number of protons must be equal to the number of electrons, so this is 56 as well. The third example, this is a different way of writing it. Okay, if we write it this way, this is the name of the element. Okay, that one's probably, at least hopefully, pretty straightforward. And then this is that mass number. Okay, now what does that mean? Well, we get the mass number, but we don't have the atomic number. What are we going to do? Well, we can look up boron on the periodic table, right? If we look it up on the periodic table, we'll see that boron has an atomic number of 5. Okay, so you should still be able to do this. You'll have your periodic table in class. You can look up boron, find the atomic number. Since it's 5, that means we have 5 protons. In terms of neutrons, we take our mass number here, 11, we subtract our 5, and that's going to give us 6 neutrons. Since the boron is neutral, that means that the positive protons must equal the positive number of electrons, so that would be 5. Alright, so that's the end of our video. Make sure that you do your online questions, your WISC, and we'll see you tomorrow.